review a few different scenarios in this video regarding the normal force. The first scenario is very simple. You have a flat surface and you have an object on that surface. So in this particular scenario, the force of gravity, which is calculated like any other force, mass times acceleration of gravity, is m times g. In fact, from now on, actually, we won't even label it as force of gravity. We'll just go ahead and directly label it as m times g. So the force of gravity is pushing this box into the surface. And if the surface is strong enough, it's going to prevent the box from going downwards. It's going to hold the box in place, meaning that the surface pushes back up with a normal force that is exactly as strong but opposite in direction as the force of gravity. So in this particular case, the box stays in equilibrium. It doesn't go down or up, it's just balanced. And the normal force is equals to m times g. Remember that the normal force is always perpendicular to the surface, and the normal force is the force that the surface exerts on the object in response to the force that the object exerts on the surface. The next scenario has the same object on a flat surface, but now we are going to be pulling on the object at an angle theta. So we're pulling on that object with a force Fa, some force, 5 newtons, 10 newtons, 20 newtons, doesn't make a difference. We're labeling it as Fa, and we're pulling it at an angle theta. When this happens, you should remember to always find out how much of that Fa is pulling the object to the right. So that's Fax, and how much is pulling it up, Fay. Keep in mind that if you're given Fa and you're given theta, you can calculate Fax and you can calculate Fay. You can calculate Fax by using your cosine functions, and you can calculate Fay by using sine. And when you calculate Fax, it comes out to be Fa cosine theta. And when you calculate Fay, it will come out to be Fa sine theta. The hypotenuse times sine theta gives you the opposite side. The hypotenuse times cosine theta gives you the adjacent side. So this is important to begin with. Next, you're going to realize, well, I still have the force of gravity pushing the box down into the surface, which is m times g. In this particular case, though, when you try and calculate the normal force, n, is actually going to be weaker than it was in the previous example, because in this particular case, the box is not pressing against the surface as much as it was in the previous example. The reason why it's not pressing against the surface as much as it was in the previous example is because in this particular situation, you are pulling the box upwards by Fa sine theta. The force of gravity is pushing it down by m times g, you're pulling it up by Fa sine theta, so the box doesn't press against the ground as hard. So the ground does not have to push up as much. So the normal force actually ends up being mg minus Fa sine theta. Remember, the box is in equilibrium on the y-axis, so all the forces pushing it down and up must end up balancing each other. And this is the way all the forces balance each other. The normal force is mg minus sine theta. The normal force is the remaining component of mg minus Fa sine theta. So in this case, normal is mg minus Fa sine theta. The next scenario, we are going to be, instead of pulling upwards, we're actually going to be pushing into the box. So we have a flat surface again, we have the box, and now we're pushing into the box with a force Fa that makes an angle theta with the horizon. So Fa is now pushing into the box with a force Fa. It could be 5 newtons, 10, 15, whatever shows up in the problem, and makes an angle theta with the horizontal component. So whenever you run into a problem like this, once again, find out how much of Fa is pushing down and how much of Fa is pushing to the left. The component that's pushing down is your y component, so you can find that out again by just doing Fa sine theta, and the x component is Fa cosine theta, except in this particular case, remember the Fa cosine theta is pushing the object to the left. In the previous scenario, the FA cosine theta is pushing the object to the right. So just keep that in mind, because in this particular case, the object may tend to move to the left. The other forces we have to keep in mind are mg. And now the normal force is going to be bigger than what it was in the previous scenario, because now the force of gravity is pushing down, and FA sine theta, the y component of FA, is pushing the box into the surface, so this box presses against the surface with a larger force. And so the surface responds back with the normal force. So the normal force in this case is mg plus FA sine theta. So that's how you calculate the normal force when you are on a flat surface. The next scenario is going to be the object is going to be on an incline. So now we have an inclined surface. And the incline makes an angle, theta, with the horizontal component. You have an inclined plane and you have this object on the inclined surface. In this particular scenario, the force of gravity, remember, always pushes down. So this is the force of gravity. The force of gravity is always going to push down. Now the force of gravity gets broken up into two components. It gets broken up into its y component and into its x component. The y component is responsible for pushing the box into the surface. The x component is what's responsible for pushing the box down the surface. If this is theta, then this is theta. And this makes a right triangle. mg, remember, pushes us down towards the ground. And mg would actually cause the box to move in this direction, downwards, if the surface wasn't present. But because the surface is present, mg gets redistributed. It gets redistributed in this direction, pushing the box into the surface, and pushing the box down the surface. This is theta, the same theta as this. And if this is mg, then the y component is mg cosine theta in this particular scenario. And the components that are pushing it down the surface is mg sine theta. The easiest way to understand this concept is, instead of using the traditional xy axes, so instead of using the traditional xy coordinate system, you take your coordinate system and you tilt it. You tilt it in this particular scenario counterclockwise, and you tilt it by the same angle theta. So instead of using the traditional xy coordinate system where the x is parallel to the horizon and the y is parallel to the vertical, what you're going to do is you're going to tilt your xy axis counterclockwise by the same angle theta. So now maybe it makes it a little bit clearer that when you look at this diagram, this force of gravity, when you draw it on your xy axis, it's actually going this way. That's your force of gravity. So that force of gravity, this component is the force of gravity on the xy axis. Thus, I can break it up into its y component and into a component that we're going to call the x component. The x component is this force that's responsible for pushing the box down the surface. The y component is the force that's pushing the box into the surface. So this is theta, and if the hypotenuse is m times g, then this component is mg cosine theta, and this component is going to be mg sine theta. So in the diagram that I've given you, the normal force is going to be perpendicular to the surface, because that's the definition of the normal force. It always has to be perpendicular to the surface, and it always is the force that the surface exerts on the box in response to the force that the box exerts on the surface. So the box is exerting a force on the surface, mg cosine theta, so the normal is also going to be mg cosine theta. So when you're on an inclined plane, the normal changes to when you're on a flat surface. On a flat surface, if there are no other forces interacting with the box, then the normal force can be equal to mg. But on a flat surface, when there are other forces pulling or pushing the box at an angle theta with the horizon, then the normal force will change. On an inclined surface, it'll definitely change. Now the normal force is equal to mg cosine theta, which is responsible for pushing the box into the surface, and that's what generates friction. And mg sine theta is responsible for pushing the box down the surface, down the incline. That's what's going to cause the box to come sliding down. And if this force is greater than the force of friction, the box is going to slide down. If this force is not greater than the force of friction, the box will not slide down. Alright, so now we're going to take the same exact scenario and we're going to complicate it a little bit more. We're going to take our flat surface, our inclined surface. We have our box. And now we are going to pull on the box at an angle pull the box. So somebody's going to push on the box in this direction with a force of Fa. So the box is sliding down, but there's somebody pushing on the box in this direction. So now how will the normal force change? Well, the force of gravity is still mg. The y component of the force of gravity is still mg cosine theta. This is theta, same theta as this. The x component is still mg sine theta. So now, when you're asked to find the force of gravity, you'll have to be careful because you'll have to break up this force also into its x and y components. So if this is Fa, you'll have to break up Fa into a component that is perpendicular to the surface. This will be theta also. This will be Fa cosine theta. And this will be Fa sine theta. So Fa will also have to be broken up into its two components. One perpendicular to the surface, one parallel to the surface. Just like the force of gravity has been broken up into its two components. One perpendicular to the surface, one parallel to the surface. And all of these are based on the principle that we have tilted our xy axis. We have tilted our xy axis from the traditional xy axis where the x is parallel to the horizontal, and we've tilted it by an angle theta. So now these forces are no longer on the traditional y-axis, but now they're considered between the x and the y-axis, so they have to be broken up into their y components and into their x components. So in this particular scenario, if somebody asks you to find out the normal force, you'll say, how many forces are pushing the box into the surface? Well, mg cosine theta is one of the forces pushing the box into the surface. The other force that's pushing the box into the surface is Fa cosine theta, which is a component of Fa. Fa cosine theta is also pushing this box into the surface, because it too is also pushing perpendicular to the surface. So in this particular case, the box is pressing against the surface with a larger force than it was in the previous example. So the normal force is going to be stronger, it's going to be bigger, it's going to be equal to mg cosine theta, which is pushing it into the surface, plus Fa cosine theta. Plus Fa cosine theta. You may get a problem like this, and they may ask you, this object is sliding down. They may ask you a question and say, this object is sliding down at a constant speed. And if that's the case, if you know the object is sliding down at constant speed and you know that there's friction involved, friction will oppose the direction of motion. So if this is the force of friction in pink, then you would know right off the bat, if the object's traveling at a constant speed, then the Fa sine theta, which is pushing the object down the incline, mg sine theta, which is also pushing the object down the incline, these two forces have to be just as strong and equal to the force of friction. If the object is traveling at a constant speed, you know this force and this force has been balanced out by the force of friction. If the object is accelerating down, then you know this force and this force are greater than the force of friction. And of course, if the object is sliding down but it's slowing down, it's decelerating, it has a negative acceleration, then you know the force of friction is stronger than these two forces, and the object's going to slow down and finally come to a rest. It's going to come to a stop. But if they say that the object's sliding down at a constant speed, then you know that the force of friction is exactly as strong as mg sine theta plus Fa sine theta. And I've run out of room, that's why I wrote it down here, but mg sine theta plus Fa sine theta are the two forces pushing us down the incline, so that's going to be the strength of the force of friction if the object is coming down at a constant speed. Finally, I'll do one more example of an object on an inclined plane. So we have, once again, our inclined surface. Angle is theta. Object is here. So we know that the force of gravity is mg. We know that the y component of the force of gravity is mg cosine theta. We know that the x component is mg sine theta. So these are the forces that are impacting the box. But then let's say another force is added to the mix, and we say that somebody is applying a force in this direction. And let's call this force Fa again. So now, if this force is coming, is in the direction as drawn, you have to now break up this force into its x and y components too. You've got to say, okay, how much of Fa is pushing perpendicular to the surface, and how much of Fa is pushing up the surface. So if this is theta, then I can comfortably say that this angle is theta also. If Fa was being applied to the box in this direction, then there's a component of Fa that is perpendicular to the surface, and there's a component of Fa that's parallel to the surface. So the component that's perpendicular is going to be Fa sine theta, and the component that is parallel to the surface is Fa cosine theta. So in this particular scenario, if they say, once again, what is the normal force? Well, you have to ask yourself how many forces are pushing the box into the surface. Mg cosine theta is pushing the box into the surface, and so is Fa sine theta, which is a component of Fa, is pushing the box into the surface. So the normal force has to balance both of those. The normal force has to balance both of those forces. So the normal force is going to be equal to mg cosine theta plus Fa sine theta. In this particular scenario, if they say that the object is moving at a constant speed, then you know that these two forces have to be taken into account when you calculate the force of friction. This force is pushing the object up the incline, this force is pushing the object down the incline. And if there is friction, then if the object is moving up the incline, then friction will be pointing down the incline, because friction opposes motion. So in that particular situation, then friction has to be the difference between mg sine theta and Fa cosine theta.